Well, hello and welcome to Advances in Emergent Needs in Paleo Geoscience Cyber Infrastructure, a webinar series organized by C4P. C4P, Collaboration in Cyber Infrastructure for Paleo Geosciences, is an EarthCube research coordination network supported by the National Science Foundation. I'm Doug Fills, and I'll be the moderator today, and Megan Carter will be running the WebEx. In today's talk, we have two presentations, each 20 minutes, with roughly 10 minutes for questions after that. We want to keep this to an hour, so I'll be fairly strict about enforcing time limits, and we'll give each speaker a 3-minute warning. If you have questions, please send them through the WebEx chat window, and Megan will read them aloud after the presentation. You may send questions in at any time. All presentations and follow-up discussion will be publicly archived on the EarthCube website and at the C4P YouTube channel at youtube.com/Cyber4Paleo. Our first speaker today is Tom Olszewski from Texas A&M University, and he'll be speaking about recommendations from the Computing with Time workshop. Our second speaker is Mike Gurnis from Caltech, who will be telling us about G-plates. We'll begin with Tom. I'll pass you the screen share, and please click on the pop-up window and begin when you're ready, Tom.
Enter now. All right, everybody can hear me?
Yes.
Okay, sorry, I just wanted to make sure because it's gotten awfully quiet. And can you see my screen?
I don't see a screen right now.
Okay, let's see what's going on here.
So you have to click Start Share Application.
Sorry, I'm not seeing anything that says, I'm seeing Make Presenter. All right, that just presented presenter privileges back to Research Coordination Networks. I think you probably need to pass that back to me.
Here. I just gave it back to you.
Okay. And I'm not seeing, share desktop. Can you now see my desktop?
Yes.
All right, thank you. Sorry that took so much
No
confusion.
problem.
All right, well, good afternoon, and thanks for turning in. I'm Tom Olszewski, as I was introduced. I was co-host with Chris Jenkins for a workshop that was held last week at UCAR in Boulder, Colorado, with a focus on computing in geologic time. This is the second workshop in the C4P RCN series. And for context, it's within the aegis of EarthCube. And although EarthCube is still defining itself in some ways, as a general statement, I think we can say that EarthCube is all things data in the geosciences. And one of the critical issues that the C4P group proposed to deal with is really a critical aspect of a vast majority, I would argue, certainly quite a lot of geologic data, that is to say specifically geologic time. One of the things that has, I think that we can observe is that the communities that provide and use geologic time information are very diverse, and they don't always communicate with one another. Nevertheless, developments over the past decade or even just the last few years have seen substantial advances in geochronology, in age modeling, and correlation that are requiring new tools and putting new demands on data. So the aim of this workshop was to focus the attention of researchers on the computational challenges with geologic time in databases, correlation software, resource catalogs, visualization, numerical modeling, and information processing. Overall, the meeting was small, had about 20 or 22 participants, but it was quite diverse and included representatives from a variety of research communities, including uranium-led geochronology, for example, database and data repository managers, statisticians, and representatives from the world of geoinformatics and computer science, as well as the expected users in, for example, paleobiology and quaternary geology. The size of the group made it possible to essentially have an ongoing conversation amongst everybody, rather than dividing into groups and then re-meeting. And in particular, because many of the participants actually span these different categories and these different research groupings, there was a lot of continuity and a lot of exchange. And I think overall, people walked away with a reasonably positive feeling for the recommendations and the topics that were covered through the 2 days of meeting. Okay, just as a reminder, I think it's always smart to start with what are the science drivers, so that we don't lose track of the overriding picture amongst the details. So why is geologic time and Earth history actually important? For one thing, and these were all topics that were discussed and overviewed at the workshop, Earth history and geologic time essentially can serve to define the initial conditions when modeling the Earth system. Related to that, this is a relatively novel topic, I think, for the larger community, but this was brought up last week. Earth history has the prospect of providing data for a data assimilation. Data assimilation generally being using data to constrain forward models as they actually run, not just initializing them and not just comparing them at the end. It's always worth remembering that Earth history preserves the outcomes of past natural experiments, and those experiments were operating at scales that are not amenable to direct manipulation of the world in the present day. These are large-scale hypotheses and regionally global systems. And lastly, it's always worth mentioning, and we should never forget, that discovering Earth's past is both fun and engaging. It's no less important or valuable than any other human endeavor. Okay, so in the scope of science drivers, the next thing is the meeting was initially sort of organized around a set of topics that we hoped would at least provide an entrance into the main issues that we would eventually discuss. These topics included collecting and aggregating geologic time data, computer visualizations for geologic time, harmonizing across geologic time parameters. I'm going to take a second to explain this one because it was difficult to come up with a phrase that helped communicate what we wanted to get at with this. But essentially, the point is that geologic time is communicated in a variety of ways. It's not just actual ages from geochronology. We also use other estimates, and we oftentimes have the geologic timescale to turn to, which is a very different way of communicating information and uncertainty than, say, a number that's estimated from an age model. So that's clearly an issue that's facing how we report geologic time and how we use geologic time. After that, we wanted to discuss legacy data resources. We wanted to discuss data relationships, particularly stratigraphic data relationships, and I'll come back to this in a later slide, specifically the topics of seriation, getting superpositional events within a single succession in the right order, and correlation, relating the succession of events in one location to the succession of events at another location. And lastly, but not least by far, was realizing and representing uncertainties about geologic time. All right. The first thing that we started off with the workshop was going around the table and asking people what their wants were. And this is my bullet-pointed summary for a slide in terms of these wants. So this has gone through the filter of my brain, but nevertheless, I think it hits the main points that people brought up. First, we definitely want to be able to intelligently access age data. We want to find it easily, and we want to be able to understand exactly what's being communicated when we access that data. We want to be able to build age models at a variety of scales. We want to be able to incorporate not just data that we've measured ourselves, but data that are available more broadly. We want to be able to assimilate data into forward models. It's likely that forward models, as they become more sophisticated, will be increasingly used to forecast Earth processes, and the data that can be used to constrain them as they run need to be in shape so that that can actually happen. We need consistent quantification and propagation of uncertainties. I'll come back to this and elaborate a little bit more about how that conversation proceeded. But it was clearly the question of uncertainty and how to report it and how to propagate it were a recurring theme throughout the 2 days of the meeting. We want full reproducibility of age models and chronologies. We need to report not just the data that were used to derive an age model, but also the parameters and constraints that went into that age model. People that build domain-specific tools, specifically software tools, would like to get full credit within the community and particularly within their academic realm for creating these tools. I think that's a very common kind of experience for academics, but it was brought up specifically in this context. And lastly, I wasn't sure exactly how to phrase this, so I borrowed words from the person who brought it up at the meeting. Somehow overcome anxiety over using geologic history. Historical science is a little bit sometimes unfamiliar to scientists who primarily work with experimental approaches or are looking at things in the present day. And being able to define geologic time in a sufficiently rigorous manner that makes that information familiar to those other communities is critical to not just being able to use that information at that level, but also essentially getting the scientific respect that the data that we steward as Earth historians get its full due. All right, so I'm going to try to avoid any more bullet-pointed lists. I'd rather show some pictures and give you a flavor for some of the material that was covered and some of the directions that the conversation took last week. One of the really critical things that came up was the power of interactive visual tools in analyzing data. One of the really convincing and very effective demonstrations of this, I think, was presented by Jim Bowring of the University of Charleston. And this is a screenshot from software that he's been involved with developing, not him alone, but he's the one who presented at the meeting, called Uranium-Lead Redux. Essentially, this is a software package that's designed to carry out data reduction of uranium-lead isotope analyses. In a sense, some of the primary information that we use, particularly for the pre-quaternary, to estimate numerical ages. And one of the real strengths of this software that I think he convincingly demonstrated is that it allows an investigator to see the consequences of different choices, including different samples in a collection of samples, changing the actual parameter values used to estimate ages. The outcomes of these different choices are shown graphically, both directly and immediately. So it's not that this couldn't be done before, but it took a couple steps. The ability to do this really allows potentially the people that are working with this data to get a much better sense of what they're trying to get at and what they're trying to communicate. Another aspect of the power of this kind of software is that it outputs the result in a standard and complete format, and it takes oftentimes data directly from automated instruments. So it even eliminates those keystroking steps. In any case, so this was a really good example of the power of interactive visual tools. Another topic that repeatedly came up in the context of the workshop was the need to track and partition uncertainty. And this isn't just limited to uranium-led geochronology. Through every step of estimating ages, from the calibration points all the way to interpolating and extrapolating those data to other horizons. This poster was contributed by Noah McLean, and it's an example of how the Earth time community that deals with uranium-lead, in this case, partitions out and explicitly keeps track of all the sources of uncertainty, variation, and error through every step of the process, from direct measurement in a mass spectrometer to the actual numerical age that they output and that other members of the community use. This kind of explicit statement has a lot of power in terms of communicating what's really going on and how well we actually understand the ages and times that we're looking at. Geologic ages are not just a matter of direct numerical age estimation. Oftentimes, those direct numerical age estimates are used to calibrate age estimates for other horizons. And that process adds an additional layer of uncertainty. In individual stratigraphic sections, for example, in building an age model from a core or a continuous outcrop, this can be done simply by connecting points in the simplest sense, although that hasn't been done for a long time. But recent developments have begun to apply sophisticated Bayesian approaches to obtaining the optimal, by some criterion, the optimal age model in an individual sedimentary succession. So this is a figure from an upcoming paper in Pages magazine from a workshop in Belfast. It was contributed by Eric Grimm, and it's a comparison between a traditional sort of age-fitting model, the red line, and this new Bayesian approach from a piece of software called Bacon, that's the blue line. What's really interesting and important, and I think was generally regarded as very valuable at the workshop last week, was the hazy gray cloud around that blue line. That effectively is a communication of the degree of uncertainty at any point. And essentially, it is a way of communicating the age and how well we know the age at each point in this particular core. So in addition to trying to estimate the ages of individual objects, which can either be done through, say, that geochronological radiometric approach or a biostratigraphic approach for an isolated collection, we can obviously be concerned about estimating the correct ages in a controlled stratigraphic succession, right? A core where we know exactly the superpositional relationships of every event in that core outcrop. But that's not we're not limited to that, and that's not the end of what we want to get at with Earth history. Another important issue is how to relate the succession of events at one location with the succession of events at another location. And one of the pieces of software that was described, although it is certainly not the only example of software that does this, was CONOP9, which was developed back in the 90s by Peter Sadler, and has gone through another number of iterations. This figure, as it turns out, is taken from the most recent issue of the Sedimentary Record, which was just put out by SCPM last week. So a very timely article discussing automated correlation and timeline extension among sites. So what Sadler is trying to communicate in this figure is, in a series of vertical successions, we can recognize the same event. An event would be something like a volcanic ash bed. It can be geochemically fingerprinted. The first appearance or last appearance of a fossil range, an isotopic excursion, or a paleomagnetic reversal. And this is simply a set of lines that connect those each of those events across a set of successions. And in this case, you can see that stratigraphy and sedimentary records are incomplete. They can be self-contradictory. Clearly, we're not looking at a set of timelines. A traditional biostratigraphic approach for this set of successions from New Zealand basically broke the timelines into these larger packages, kinds of intervals or zones, which are a really important way of communicating the age of an individual collection. But with current computational advances, essentially what the software can do is come up with a set of timelines connecting events and extending the timeline of each event to its most likely position in each of the cores. So this is an example of that output. Each of the lines connecting the vertical successions is effectively a timeline. So in some ways, it greatly resembles the biostratigraphic zones that were shown in the previous version. But in this case, we can actually begin to see architecture within each of these intervals. For example, unconformities, downlaps. It's a much higher resolution understanding of geologic time in that same succession. And importantly, each of these extended timelines has an uncertainty around it. Although it's not depicted in this image, because that would make it too much of a mess, essentially we have an idea of not just the best place or the optimal position of a horizon, we can actually get an error bar around it.
Tom, about 2 more minutes.
Thanks, Doug. I'll just be finishing up. Speaking of Doug, at the meeting last week, Doug actually presented a recoding of the CONOP9 software to parallelize it so it can operate more quickly with even larger data sets. He presented a very nice example based on ODP and IDP data from the Pacific. In the end, I boiled this down to basically 4 recommendations. This is sort of a draft version of what will come out in the ultimate report. Recommendations from this group include that we need to establish critical metadata fields for geochronological data, and we need to facilitate passing age control and age model information through the entire process, from where ages are estimated to where they're used. Potentially, this information could follow samples through the use of international geo identity numbers, IGSNs. We need to foster development of interactive visualization tools to do a variety of things, to build age models, to automate seriation and correlation and build temporal frameworks, and to view geological and geoscientific data in a fully resolved time-space framework. The third recommendation is to define or adopt a common framework for levels of data derivation. We need to acknowledge that what is considered a result of analyses from data at one stage actually becomes the data that's incorporated into analysis at another stage. And lastly, we need to keep track of and propagate uncertainties from initial direct measurements all the way to the subsequent steps to the derived product. This was a recurring theme throughout the 2 days, and increasingly, as we use quantitative approaches to estimate ages, how to do this and what the quality of our uncertainty is will become easier to carry out, but it will also demand more of the data that we're inputting in order to develop geologic time frameworks. And at this point, I'd be happy to address any questions or take any comments from others who participated in the meeting last week.
Thank you, Tom.
Okay, do I need to send back, let's see.
Oh, I can transfer.
You can still host.
Yes.
Okay.
We were just going to see if anybody had any questions. I don't see any in the chat window. But that would be the place to put it if anybody has anything they would like to ask.
Well, as always, when I lecture to classes, I will take the absence of questions as a victory in the clarity of the presentation.
Hold on just a minute. There's a question.
Excellent.
Tom, what do you see as next steps or desired further efforts after this meeting?
I think that we have these general recommendations, but I think, so the C4P RCN has one last synthesis meeting to bring things together. And I think that that will be an opportunity to actually come up with recommendations to implement these. How do we encourage people or enforce, if necessary, reporting the appropriate kinds of data? How do we communicate to people what the appropriate kinds of information are? We need to come up with mechanisms, as I sort of described. These interactive visualization tools are phenomenal. These automated time-space framework tools are incredibly powerful. They're slowly becoming used more widely in the community, but we also need to encourage people to essentially adopt them, to make them basically commonplace, so that we have, we take full advantage of the power of this data and the power of these software tools. So that's my, beyond the vague recommendations, where would I like to see this go? I would love to see more and more usable, downloadable software and easier access to well-compiled data, which I think is where we're going as a community.
Great, thank you, Tom. All right, well, if there aren't any more questions, and by the way, Tom, your presentation was very clear, thank you. I will pass the ball to Mike Gurnis.